So after that last fiasco, I did at least take a moment to look at this and make sure we had reducible, irreducible quadratics. Sure enough, I feel good about this one. There's nothing that multiplies to 2 except for the numbers 1 and 2, or -1 and -2, and they don't add up to 1. So that does not factor. And then the other term here, the other factor in our denominator is our sum of squares, which also doesn't factor. So I am happy. We now have two irreducible quadratics. These cannot be factored down into linear pieces. We are good to go in terms of setting up our partial fraction decomposition. So we go, all right, well, I see this. I see it. It looks like, I'm going to get mad. I want my black pen. It looks like we're going to end up with two separate rational terms over here, both of them with quadratics in the denominator, which means that we need to remember that we need an entire linear component in the numerator. So we need an ax plus b and a cx plus d. Again, try it out without the linear term. You're going to realize I don't even have enough, I don't have a large enough degree to even possibly equal that original function's numerator. So we go, okay, all right. Let's multiply everything through by that common denominator, which is everything we had before, our x squared plus x plus 2 times our x squared plus 1. Well, we know on the left-hand side, we're going to get right back out that original numerator as the denominator will cancel out or turn into a factor of 1, right? And then on the other side, ooh, we can do it. We're going to get that ax plus b, and it's going to be multiplied by that other piece. We do need to make sure that we put parentheses around it because we are going to have to, unfortunately, distribute all this out to each other. And then the same thing with the cx plus d. It's going to, right, the x squared plus 1s will become a factor of 1, and we can rewrite that. But this is what we're going to have here. So already we are sad. And when we were in class, we sort of realized bad things happen too. It wasn't the best for either method. This is just a really unfortunate question. It just comes down to whichever one you like. Unfortunately, because we don't have nice pretty zeros from our linear factors, if we're plugging in x's, we're going to just plug in random x's to create equations for this system that we're making. So we have two ways to make that system. We can still go with the book method, which means I'm going to start out. I'll even put a line here. I have this 2x cubed plus 7x plus 5 is equal to, I got to distribute everything over there. It looks like I got an ax cubed plus ax, just distributed that to both of those other terms, plus a bx squared plus b. I still got to do the whole second piece of this. So it looks like I'm going to get a cx cubed. Might as well line things up. Oh, I should have done that other one in a different order. It's too late now. But that's going to end up with cx squared. I'll just put it under that. Plus 2cx. See, this is I'm just making sure they all line up. I really, you know what? I'm going to go backwards in time. I'm going to rewrite the top one. It's gonna keep bothering me if they're not in descending order. So I'll do the bx squared, then the ax, then the a. So that way we have everything, and I can just sort of line these up horizontally, so that'll make life easier when I do that coefficient grabbing. So this is plus cx squared plus 2cx. And then we have the same thing with the d's. We got plus dx squared plus dx plus 2d. So we can add up everything on that the right-hand side. I guess we don't even need to add it up because now we're ready to figure out our system. We got to find all the x cubes, all the x squareds. This is a nice thing about me having lined them up. All of the x's and their coefficients, and all of the constants and their coefficients. So for the x cubed, I can see I'm going to end up with a 2 as my result. And there's only two things that give me x cubed, the ax and the cx, the ax cubed and the cx cubed. So this has got to be a plus c. There isn't an x squared on the other side. So that means there's technically a 0 over here. but I have a ton of things that are x squared in my right side. So it must be b plus c plus d. All of those must cancel each other out so that there's no more x squareds. Then we move on to our x's. So for our x's, we've got 7 is equal to a plus 2c plus d. And then for our constants, that's our 5. We just have 5 is equal to a plus 2d. So this is when it's like, gross. I could do um, lots of stuff. I mean, it's not terrible, but I theoretically should be moving through solving the system of 4 unknowns. This is when, if you had technology, to me, this is the only time I've ever used reduced row echelon form. I would set this up as like, okay, 1a, 0 b's, 1c, 0 d is equal to 2. No a's, a b, a c, and a d is equal to 0. 1a, no b's, 2 c's, 1 d is equal to 7. 1, 0, 0, 2 is equal to 5. And I would have the calculator tell me what that solution was. So with the Desmos calculator, I'm just going to make a calculator that's that augmented matrix. I'm going to tell it, oh, I don't really want a new matrix. That was a lie. Let's say enter. And then I want to give reduce row echelon form of that matrix. So I can see there are my solutions. I can even press the fraction button. It appears my solutions are a is equal to negative 1/3. B is equal to, and at least this gives you a way to check if for some reason you were forced into doing this on a different question. Oops, that's going to take a moment to reload. That you'd be able to sit there and be like, okay, negative 2, 7/3, and 8/3. Negative 2, 7/3, and 8/3. You could, of course, at least check your work with that. So again, if you were doing this the clever way is going to fail us a bit. We can still do it to create our system of equations, or at least get part of the way there. This is when we'd have to just choose x's that are easy to plug into this. So 0 is always easy. We'd have 5 is equal to, the a would go to 0. We get b times 1. C goes to 0, so we get plus d times 2. So we have this, 5 is equal to b plus 2d. Doesn't help us, right? We have one equation, 2 unknowns. So we'd have to be like, okay, let's plug in something else. Let's plug in maybe a 1, see what happens. X is equal to 1. Well, then we'll have 9 plus 5, we'll have 14 on the left-hand side. We will have a plus b times 2 plus c plus, so we'll get a c plus d, because again, that x is 1, times 1 plus 1 times 4. So now, ooh, is that any better? Oops, I left 2 off that. I mean, we could FOIL, like, distribute these things, but great. And so now we just have, I mean, all we're doing is building a different system of equations that tells us the same thing, and we have to plug in to do it. So of course we could try like an x is equal to negative 1. That's probably going to be the next least sucktastic thing to plug in. And we'd have to have at least, probably, unless we get lucky, 4 different things to plug in to get our 4 equations to create a system for our 4 variables. So you need as many equations as you have variables, and when you're adding up these coefficients using the coefficient method, you're guaranteed to get that. Otherwise, you just have to plug in x's to create 4. And here, we're still back at this, except for it looks like we're going to end up with an uglier, beefier matrix than what I ended up with when I did the method out of the book. So again, pros and cons, right? This is like synthetic division versus long division. Like sometimes it's great and it's fast to do synthetic. Sometimes it doesn't work. The nice thing is the other method of plugging in will always work. It's just that it might end up being more work. So taking that moment to really decide what to do. So we have one last example, and that's repeated quadratics. So let's see that next.